In many people's minds, atoms appear as tiny balls. When viewed under a scanning tunneling microscope, these balls seem to line up neatly. To a certain extent, this is true. However, these tiny spheres that we observe are actually probability clouds of electrons surrounding the nucleus, indicating the likelihood of finding an electron at a particular location. When not directly measuring an electron, it appears as a cloud in multiple places simultaneously. At the center of this electron cloud is the atomic nucleus, which accounts for almost all of an atom's mass. If we were to liken the nucleus to the yolk of an egg, the electron cloud would be like the egg white, but the volume difference between the two is much more extreme than that between an egg yolk and its white. Compared to the size of the entire atom constituted by the electron cloud, the nucleus is unimaginably small. Rutherford's gold foil experiment, where he bombarded gold with alpha particles, gave an approximate measurement of the nucleus as being only about 1/10,000th the size of the whole atom. This indicates that the real interior of atoms is incredibly sparse. Almost all the physical and chemical changes we witness in our daily lives are not directly related to the atomic nucleus. These changes are due to interactions between outer electrons. For instance, the different sensations we feel when we touch objects are due to electromagnetic interactions between the electrons in our hand and those on the object's surface. Likewise, chemical reactions are interactions between outer electrons of different atoms. Thus, before delving deeper into the intricacies of the atomic nucleus, it's essential to understand the characteristics of electrons. Bohr's atomic theory was primarily about electron energy levels. However, a question remained unanswered: why don't electrons all gather in the lowest energy level? This not only puzzled Bohr but also troubled many young scientists, including Wolfgang Pauli. As a graduate student, Pauli, who was adept at relativity, once boldly pointed out a mistake during Einstein's presentation. Having worked with Sommerfeld and Born, and later briefly with Bohr, Pauli was deeply pondering the electron arrangement issue. He eventually proposed two assumptions. First, no two electrons can be in the exact same quantum state, leading to the Pauli exclusion principle. Second, apart from spatial properties, electrons have an odd angular momentum property, later known as spin. Inspired by spectral data in 1924, Stoner proposed an electron arrangement theory. Drawing inspiration from this, Pauli formally introduced the Pauli exclusion principle in a 1925 paper. At 25, this work later earned him the 1945 Nobel Prize in Physics. Let's park the Pauli exclusion principle for a moment and delve into spin. Inspired by Pauli's principle, Larmore's assistant, Ralph Kronig, once proposed to Pauli that electrons might possess an angular momentum stemming from their spin. Pauli immediately refuted this, arguing that if electrons had spin, their surface line speed would surpass the speed of light, violating the theory of relativity. Kronig then abandoned publishing this theory. However, around the same time, two Dutch physicists, Goudsmit and Uhlenbeck, also proposed the concept of electron spin, receiving validation from heavyweights like Bohr. The entire physics community jumped into the discussion. In fact, the phenomenon of spin was detected as early as 1922 in the Stern-Gerlach experiment. But at that time, quantum theory hadn't evolved enough, so its significance remained elusive. In the original version of this experiment, silver was heated to evaporation. This vapor then passed through a series of control valves to form a beam of silver atoms. This beam then passed through a magnetic field before hitting a screen. Classical theory suggests that since the electrons within an atom orbit the nucleus, they should exhibit a magnetic moment. Given the random nature of these moments, when passing through the magnetic field, the expected result would be a continuous line on the screen. Instead, two distinct spots appeared. It was later realized that, while electrons orbited the nucleus, they also exhibited a spin of their own. This spin is distinctly different from the spin of planets. For planets, spin is an external attribute that can vary in speed. In contrast, for subatomic particles, spin is an intrinsic property, also known as a degree of freedom, in physics. If a particle's spin value changes, it's no longer the same particle. Instead, it has transformed into another particle. While the rotation of a planet is continuous, the spin of an electron is discontinuous. It has angular momentum values of only 1/2 and -1/2. This is akin to saying it must rotate twice to return to its original position, similar to a Mobius strip where one must travel 2 full loops to return to the start. This might explain the appearance of 2 spots on a screen, but physicists at the time still couldn't understand how electron spin originates or what these values truly signify. The final answer came from another genius in the world of physics, Paul Dirac, but we'll get into that later. Although it was puzzling to many what spin truly was, Heisenberg, who was researching matrix mechanics, believed that in studying physics, we should focus only on measurable quantities and not overthink the unmeasurable. With electron spin, what's observable is just its angular momentum value. The actual mode of its spin is immeasurable, so there's no need to obsess over it. Spin, as a quantum state, can be thought of as a manifestation in the abstract Hilbert space. It has no counterpart in classical mechanics, making it futile to seek a macroscopic analogy, much like the later definitions of quarks having color and flavor degrees of freedom. Now, let's discuss the Pauli exclusion principle. To describe how electrons are arranged, 4 quantum numbers are needed. First, the principal quantum number signifies the electron's energy level. Then, within the same energy level, multiple orbitals can exist, represented by the orbital angular momentum quantum number. The term orbital is a bit misleading since, in quantum mechanics, the traditional concept of an orbital doesn't exist. Here, orbital means electron cloud, and its shape essentially indicates the shape of the electron cloud. Additionally, there's the magnetic quantum number, indicating the orbital's direction, and the then unnamed spin quantum number. Pauli deduced that electrons in the same orbital, having the same first 3 quantum numbers, can't have identical states, meaning they can't have the same set of 4 quantum numbers. Since electron spin only has values of 1/2 and -1/2, only 2 electrons can exist in the same orbital. This is the Pauli exclusion principle, which might sound perplexing. But let me give you an analogy. Consider an atom as a classroom and electrons as students. If a positive spin indicates a boy and a negative spin indicates a girl, they must stand in formation with different genders in the same row. So, a formation will have alternating boys and girls. As you add more students, the formation grows longer. The outermost electrons, or those in the back rows, are more active. They often interact with electrons from other classrooms, which is the basis for the varied chemical properties of elements. Without the Pauli exclusion principle, electrons would all crowd the lowest energy orbitals, leading to atoms with nearly identical chemical properties, hence, a monotonous world. The Pauli exclusion principle also explains why matter can't be infinitely compressed. But under extreme conditions, like in the later stages of a star's life when nuclear fusion isn't enough to counteract its own gravity, electrons are ejected from their orbits, becoming free electrons. The vast spaces between atoms disappear, leaving atomic nuclei floating in a sea of electrons. This dense state is what's found in white dwarfs. If you further compress this electron sea, electrons are forced into the atomic nucleus, neutralizing with protons to form neutrons, leading to neutron stars. Can a cluster of neutrons be further compressed? Some theories suggest that the neutrons might break apart, freeing the quarks within, resulting in hypothetical quark stars, which are between neutron stars and black holes in terms of extremity. But for now, they remain theoretical. In conclusion, we understand that chemistry exists due to the Pauli exclusion principle, which arises from the electron's intrinsic spin. Yet, the origin of spin remained a mystery. However, the vacuum period of the quantum era was about to end, as modern quantum mechanics, represented by matrix and wave mechanics, was about to unveil a new chapter for the quantum era.